Welcome to the pre-recording of lecture 26 of MCS 481. Today we are going to introduce the Delaunay triangulation, starting from a motivation height interpolation when modeling a terrain. I will, just like with Voronoi diagrams, scipy provides a very quick way to generate many examples of Delaunay triangulations. We will define triangulations of planar point sets. So we have encountered triangulations already, but we will see that there is still that we haven't defined yet. Um, the main result of this lecture is to arrive at a definition of the Delaunay triangulation as a result of an optimization problem. Okay, let's get started. So by the way, I pronounce Delaunay as the perhaps more Americanized version, not Delaunay, even though we use the French spelling of the word, but the name is Russian and the spelling looks French, but since it is Russian, we should not necessarily pronounce it like in the French Delaunay, which I've noticed is also a French painter. So Delaunay, what is a Delaunay triangulation? That's the main goal of the lecture. So let's first look at a problem. So we want to do some terrain modeling. So we have a set of points, and for every point we have a height measured. So it's actually a mathematical modeling question. How do we represent the height of the points outside the sample set? So we cannot obviously measure everywhere. And the sample set might also be kind of a little bit irregular. It's a little bit similar to how we started arrangements of lines where we had the rasterization problem from computer graphics. Here we do height interpolation, and we're going to determine the intermediate points via a triangulation. So we take triplets of points. If you have only 3 points, that's the only thing that you can do. You look at the plane through these 3 points, and then you evaluate the height is then the height that you get from this plane. Okay, so here it is. You have many points in that where you know the height. So you figure out the triangulation. And then for every triangle, so for every point in the plane, you can locate the triangle. And then with that triangle, you can determine the height relative to the corners of the triangle. So this is in another way, so you are having samples and you are modeling the terrain via a piecewise linear surface. Now, so you can also see this as geometric modeling. You have sampled points and you want to represent the surface as best as possible. So we will arrive at an optimization problem. So let's first determine what the right thing to optimize is in terms of this height interpolation. So let's look at an example. So we have a quadrilateral, 4 points, 4 green points, and the numbers next to the green points are the heights. So we have 2 low points, 0 and 10, height 0, height 10. And then we have 2 very high points, 1000 and 900. Now look at the middle, the point Q. what should be the height of Q? Well, first, imagine that point Q. Does it lie in the valley between, if you would connect the lowest points, and if you would interpolate with these 2 points, then you would imagine that there is a valley. So the height would be 5. So on the other hand, the other choice is that the height would be 950 if you imagine the point Q to be on the mountain ridge. So which one is now better? Well, on the left picture, you would have a very narrow valley between two spikes. In the other possibility, you would have a mountain ridge. So either you have a very deep fold or you have somehow a glowing mountain. So this introduces the optimal triangulation to maximize the minimal angle of the triangles. And I should probably have introduced this earlier. If you look from the left and the right, what is distinguishing them, so the looking wrong, looking better is subjective, but we will arrive at an objective criterion by looking at the angles. So in the triangulation that we said that didn't look that looked kind of wrong. In some sense, if you like scenic landscapes, so you could indeed imagine a river flowing between two very tall mountains, but the fact that these landscapes are scenic, that they are stand out, is that they are so implausible. So, but what I was going to say is that at the implausible, the narrow valley, you have very tiny angles. So if you look, say here, so you have very tiny angles. So the angles are actually half of what they are here. So the thing is, we want to that the minimal angle is actually maximized. So we want triangulations where all the triangles are actually not really that sharp. And the so that's actually, does this exist? And also, does this problem have a unique solution? That's another thing. So we will talk about the Delaunay triangulation as the optimal triangulation that maximizes the minimal angle of the triangles. So that's the essence of the lecture, that we get to this mathematically. Although in practice, how do you actually compute the Delaunay triangulations? So we are all familiar with Python and the ecosystem that contains NumPy, SciPy, Matplotlib. Here you see the imports, the 3 imports from NumPy, SciPy, Matplotlib, and then 4 lines, and I don't think it can get any shorter. 4 lines are essentially showing you the Delaunay triangulation. So here is the Delaunay triangulation when I prepared the slides, but I also have a notebook, and perhaps I should keep on running this notebook. So you see here I have 10 random points. If I run this again, I have another random configuration. And let me do it one more time again. So you can see, or one more time again, and you can see that we can do this as many times as we like, and we see many, many examples of the Delaunay triangulations. Notice that we can still have very small and tiny angles. What is also what should also now striking out is that every angle, every sample point is actually there. So if you count the blue points, these are the 10 blue points. So these are triangulations. Imagine again think again about the height interpolation. We want to use every single data point. Okay. There is much more that we can query. So we can query the coordinates of the points. The points are labeled from 0 to 9, so you can get all the simplices. So they're called simplices because we are thinking actually in higher dimensions, but the simplex is a three-dimensional triangle. Um, so you see that the first simplex here that is listed is made of the points 8, 0, and 7. And you can find the coordinates, so the next to last point, the point before that, and the first point, so 8, 7, 0. They are supposed to be in order, so you can, for every simplex, you have the neighboring simplexes. -1 indicates the outer face. And there are also the equations. So we've seen equations also when we talked about duality. There is also a construction that Q-Hull uses, so it's very useful to look at the documentation now. So you see Q-Hull is being used. You can pass Q-Hull options. Um, and you can see the equations. So here the equations are defining the hyperplane equations. So in some sense there is already a first algorithm that we won't see now because in this course we deal with three-dimensional convex hulls much later. Well, not that much anymore. So we have to wait till chapter 11. Now we start chapter 9. So the computation that is done in scipy uses Q-Hull, and that is used by lifting the points on a paraboloid. And that will give you if you project down these triangles, then you will get the triangulation. Okay, that's should more. So what is actually most important for this introduction are these instructions here. At this point in time, we can see many examples of Delaunay triangulations. And they are very important in various areas of applications. All right, what do we actually now mean of a triangulation of a planar point set? What is important here, again, with every point is actually important. And we therefore talk about a maximal planar subdivision. So what is a maximal planar subdivision? If you add one more edge, then you won't have a planar graph anymore. So we've used results from graph theory. A graph is planar if you don't have edges crossing each other. So a triangulation is actually a set of non-overlapping triangles. So if you would have edges that are overlapping each other, that are two edges between vertices, if they would intersect each other, it would imply that you have overlapping triangles. And that is not a triangulation. So maximality means here you have the maximal number of edges. Um, so a triangulation of a point set means actually that the vertex set of this triangulation is actually the given set. So it's important to here point out with the convex hull problem where we have vertices in the inside of the polygon that don't really matter, so they disappear from the output. Here actually we do have, and in our height interpolation problem where we started with, in the height interpolation every measurement mattered. So we don't want to throw away any points. Okay, maximality means that we have to be a little bit concerned about complexity. So what is now if the size of the input is n, what is going to be the size of such a maximal planar subdivision? Okay, let's first think about this a little bit. The 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 previous slide was actually not mentioning triangulation. Let me go back here. Well, except for the title. So, but in some sense, the words of the definitions were maximal planar subdivision, not really triangulation. So we've seen many subdivisions, for example, trapezoidal maps. They're also subdivisions induced by line segments. Here, they were not triangulations. Here, and they were also not maximal. So the first exercise actually asks you to prove this proposition. If every face is a triangle, then the subdivision is maximal. What actually means that if you want to add one extra edge, you actually lose the planar property. So what in proving the above proposition, that's the exercise, you have to write down in your proof what does it mean to be maximal for a subdivision. So subdivision is maximal that if you add one more edge, you can choose whichever pair of vertices you want. It should be an extra edge. It shouldn't be saying cheating, I'm going over an existing edge. No, if that happens, then you would have, uh, if you add one more edge, you don't have your original subdivision was not maximal. So you can start by contraposition, for example. Suppose the subdivision is maximum, then actually it means that you have somewhere a trapezium sitting in there. Because you can add one edge and you still have the planar subdivision. And therefore, not every face of the subdivision was a triangle. So that actually proves it. The main purpose of the exercise is that we think about the maximality and the planarity. Okay, okay, so the entire vertex set is actually the entire point set on input. Um, so I should have stated this differently, perhaps. We showed earlier that if your polygon is convex, then constructing a triangulation is straightforward, and we also know that there are n minus 2 triangles and 2 n minus 3 edges. So you have the extra edges that you add, but you have already the edges between the original points. So getting to these counts, this is actually what we had before. However, now that we want that the entire vertex set, or the vertex set is the entire point set, we have more triangles. So actually, we have about double the amount of triangles, except that we still subtract k. We also have more edges. Now, in some sense, the theorem is a very nice theorem. The 2 and the 3 are constants, and they're actually still in front of the n, so it's still linear. So our triangulation, um, and we now work actually with triangulations that have the vertex set p. Uh, that set has a complexity that is linear in the input. It's not as simple as the convex points, but it's of similar complexity. Okay, how do we prove this? Well, we apply Euler's formula or the Euler characteristic as well. It results from graph theory again. The number of faces minus the number of edges plus the number of vertices equals 2. So the number of vertices is the size of the input set. The number of faces, and that's what we want to bound, is the number of triangles plus 1. Why the plus 1? Because there is the outside face. So m is the number of triangles. Okay, so what do we have then? So the number of edges is 3 times the number of faces plus k, because k is the number of outside edges. So I said really because k was not defined on this slide. In some sense, you should actually go back to the previous slide. The statement of what we're trying to prove is not on this slide. But we said that we have k is the number of edges on the outside. So that's the really that you have to check. If we count this plus k, then we would double count. So that's why we defined by 2, because every edge is shared by exactly 2 triangles. Okay, we have the number of edges in function of the number of triangles. So now let's apply Euler's formula. So here we have Euler's formula that we can solve in function of m. So the m actually is the number of triangles, and that's actually what we wanted to prove. That's one of the statements that we wanted to prove. M equals 2n minus k. Perhaps let me go to a two-page format if that is possible. Yeah, actually it's not. It's more or less. So here you see the statement. So k is the number of points on the boundary of the convex hull, also the number of edges, if you remember convex hulls. So what we wanted to prove is that we had 2n minus 2 minus k triangles. The number of triangles equals m. And then we wanted to prove that the number of edges is 3n minus 3 minus k. And that follows via a simple substitution using this formula here. So once we have m, we can plug in the m, and then we have the number of edges. Notice that these are sharp bounds. In some sense, as an algorithm developer, the complexity, you have a fixed number of elements that you need to compute. So in some sense, there is not the unexpected output size. There's also not really the upper bound. No, where you have special cases. No, here it's very regular. This is kind of nice. Okay, let's now look at the um, angles. Let's get at an optimization problem. So for any triangulation, you can look at all the angles. So you look at all the triangles. So every triangle has 3 angles inside. So you have 3 times m angles. So we just label all the triangles in order. And we have a vector, a big vector, that we order lexicographically, just like in a dictionary. So we order angles from large to small, or we can order them from small to large. So it's kind of important that we are being able to compare 2 triangulations. So what we want to figure out, what is actually now the best triangulation? The best triangulation if we want to model a surface. If we have somewhere a terrain, we have measured heights, we want to model how the surfaces look like. What is the best shape that we're going to use in our modeling? Okay, so if there is an order, so any 2 triangulations can be defined that way. So notice that the number, so that's an important consequence as well. Why is this well defined? Well, the m is fixed. So once you fix your point set, your size of the um, triangulation is fixed. So it's difficult to compare vectors of different sizes. No, we always have the same size. So that's an important thing. That was the reason why the previous theorem was really a theorem. So it's something that we have to remember. So we have the well-definedness of this angle vector. So for every triangulation, which is maximal, uses every point in the given point set, we have this vector, and we therefore can actually define an optimal triangulation. So there we have an optimal triangulation if that um, angle vector is the largest. There might be other ones. So the optimal is actually not really a good word. So it's an angle optimum triangulation. So the optimum is not unique. Okay, so the exercise 2 invites you for an example of a point set. It shouldn't be a triangle, it's not that simple, but it's just as simple as thinking about 4 points and think about symmetry where one is the same. So what you need to do to solve this exercise is to draw it and actually really spell out the angle vectors, um, and say that for the two triangulations you will actually have the same angle vectors. So therefore, they're both optimal from the perspective of making the smallest angle as large as possible. And such examples are not difficult to find. You can think about this now, think about exercise 2, but we will introduce edge flip. So, okay, so we can start with any triangulation and start to modifying this. If you optimize something, you can gradually improve your triangulation. So if we look at this quadrilateral from the beginning, then any quadrilateral has two triangulations. I should say that any quadrilateral where the point sets where you don't have a point at the inside. The convex hull of these 4 points includes the 4 points. So if you flip, so you replace the edge CD by AB, you have actually a better triangulation. So you can go from the left to the right, but the flip can also be undone. So you can flip from the right to the left. So you can go in both ways. So this is called an edge flip. So going from T1 to T2. And if you're still thinking about the exercise, think about a square ABCD. Here actually we clearly are better off if we go from left to right as far as the smallest angle goes. But if you have a square, then actually it doesn't really matter. So that's the point of exercise 2. Okay, so here is where we consider illegal edges. So if we consider two adjacent triangles, so the triangles share an edge, then one of these edges is actually illegal if the minimum of all the angles in of the two triangles is less than the minimum of all the other angles. So I'm reading the definition here, but perhaps better if you look at the picture. You kind of can see that the triangulation of the right is actually a better triangulation than the one at the left. So the alpha 1 is definitely less than beta 1. And perhaps if we compare alpha 1 to beta 2, then actually it seems that alpha 1 is probably still smaller. So we have some large angles here that we cut in two, but as we cut them, they may not be get that small as alpha 6 and alpha 1. So I can't really tell. It seems now that alpha 6 is the smallest angle, but the smallest angle is actually smaller than the beta 2. The beta 2 seems to be the smallest angle from the other triangulation. So therefore, the edge here is Py, Pj. It is an illegal edge. Okay. How do we detect those illegal edges? So this is the circle theorem of Thales. So if we look at the side AB, so we have an edge AB, and then we look at the points, the triangles, where the other vertex is R, Q, and S. You see that the angles are getting smaller and smaller. So we have the angle PQR here in the definition. So, but actually where we look at are the angles ARB, APB. P is lying on the circle. So it's a theorem that is used to decide whether a point lies inside or outside the circle. So we consider the circle that is defined by the points A, B, C. So we know that these 3 points uniquely define a circle, but we can determine whether a point lies inside and outside. Doing this algebraically would be to get the equations of the circle, but this was a theorem of antiquity, and Descartes was not yet born at that time. So you can solve this problem determining whether a point is inside or outside by comparing angles. So this theorem is here written in a very, so there are statements that asks you to compare the angles APB, AQB. So Q is at the boundary when the angles are the same. So the angle between A, Q, and B is the same as A, P, and B, which in some sense doesn't seem that right to me. No, I mean, there might be something here that is not right, and I'm now able to confuse myself. But in any case, you can see that ARB, so that angle is actually larger than the angle AQB, and is actually larger than the angle ASB. So I'm not entirely sure here about this equality, which seems a bit off here, but the comparison between SQR definitely holds. Okay, so for any point on the circle, I think what is meant here is that as you move, so the P was used here for the definition, but this would be mainly if you would be moving outside with P or moving inside to R. if you are moving in the diagonal direction, along the direction of the diagonal through the center of the circle. Okay, or perpendicular to the line. Okay, so here, what is the line now? The line is the reference point of an edge. So how can we decide whether an edge is legal or illegal? Just by comparing angles. Well, um, here, and this is actually a solution to exercise 2, by the way. So here you can see that if you have the edge PIPJ, or if you replace it by the edge PLPK, it won't really change the angle vector. So you can determine here that if the angle um, PIPLPJ, if that is larger, then actually the edge is illegal. Larger than PIPK PJ, then you're better off by using this edge here, doing an edge flip. Okay. Um, Exercise 3 asks you to write pseudocode. The main goal of that exercise is for you to decide whether the circle theorem has practical value, in the sense that you can do this in a constant, quick operation of times. So you may have to dust off your calculus books and look at the angle between two vectors. So this goes back to vector calculus, where you can use the vectors to compute angles. Okay. Um, so we have a criterion to decide via the application of Thales circle theorem. We have an application to decide whether to flip or not to flip. All right, we have a function that runs in continuous time. We start from any triangulation, and at the end we will have replaced all the edges that are illegal. So we end up with a legal triangulation. It's important here that with every edge flip, the angle vector will actually increase. So the smallest angle will actually become larger. So we have a more optimal triangulation. So it is an algorithm. So every steps are unambiguously defined. So the we have a structure where we can determine whether triangles are adjacent to each other or not. We can replace the illegal edges. So we have a criterion to do the test whether an edge is illegal. So for all the edges in our triangulation, we check the triangles they belong to. So think again about doubly connected edge lists. So when we find an illegal edge, we replace it. It does terminate. Why? Because it cannot go on forever. Because with every edge flip, we had an illegal edge, so we had actually an improvement over the angle vector. So it will increase. And if it doesn't matter, if you have either way, then you won't do nothing. So you won't flip back and forth between triangulations and never get into a loop. Okay, so then what is a Delaunay triangulation? So the book keeps a little bit suspense here. So it goes on to the dual graph of a Voronoi diagram, defining the Delaunay graph. So that's what we will do in the next lecture. But the main result is here that this outcome of the algorithm, so the algorithm terminates, that algorithm, the result of that is actually the Delaunay triangulation. It maximizes the minimal angle. So it's not entirely correct to talk about the Delaunay triangulation because it's not really unique, but for the purposes of this lecture, it will suffice. All right, so what have we seen this? We know already how to compute things via scipy. Next time we will see that if you can compute a Voronoi diagram, then actually you can compute a Delaunay triangulation. They are related to each other, or if you can compute the Delaunay triangulation, you can actually compute a Voronoi diagram. Or Q-hull quickly constructs the convex hull of a three-dimensional point set, and that can be used for both Delaunay triangulations and Voronoi diagrams. So we will get to that construction as well. Okay, the main point is thus of this lecture, what is a Delaunay triangulation? So it is a triangulation that's very useful in many applications where geometric modeling is used. So if you have taken sample sets of some object, can you model the surface? So useful for geometric modeling and many other applications. So last thing that I want to show is the connections with Seagal. So here is the documentation page. So if you go to the manual in the package overview, click on triangulations. So triangulations, you see automatically Delaunay triangulations. So I mentioned a doubly connected edge list, which can be used, but there are actually specific data structures for this. Perhaps I can look at the uh, documentation. So the documentation for triangulations is extremely extensive. This picture already indicates the circle. So we've seen the circle theorem of Thales. We already have seen the circles from the Voronoi diagrams. They will come back here. Um, so we can look at the pictures. So here you see uh, definitions and data structures. So how the triangulations are represented. The flips, so here you see how also the neighboring information is defined. So flipping an edge here, how this can be done very quickly with this data structures. Yeah, so that is mainly it. And here you see the Voronoi diagram. So we will get to this next time. So you have the Delaunay triangle and the Voronoi diagram. And here you see the concept of regular triangulation. So the weights that come from the paraboloid. Um, and there are constraints also as well. Okay, so most likely for a first introduction to Delaunay triangulations, this should suffice. It should be more than enough. Um, and there's still more to go, so we will just in the next two lectures, so we can still spend two lectures on Delaunay triangulations. In the next lecture, we will see the connection with Voronoi diagrams, and we will also see an algorithm. Yet an algorithm if you are starting from if your thing is to compute Delaunay triangulations, you don't want to go via convex hulls or via Voronoi diagrams. You can construct algorithms that immediately go to construct the Delaunay triangulation. This has the advantage that you can work with specific data structures to represent triangulations.